Hi there. Today we're looking at VirTex, Learning Visual Representations from Textual Annotations by Karen Desai and Justin Johnson of the University of Michigan. So this paper at its core is pretty simple. On a high level, it proposes to take the task of image captioning, which is where you're given an image and you're asked to produce a caption for the image, and basically train a model to do this, and then just take the visual part of it as a baseline to transfer learn on other visual tasks. And that appears to work surprisingly well if you don't have much data. So if you don't have much data to pre-train on, this appears to work very well. All right. As always, if you like content like this, then consider sharing it out, subscribing to the channel, or tell me what you think in the comments. So, as I already said, the idea here is pretty simple. So people have been looking for pre-training tasks for visual tasks. So a visual task is anything where the input is an image, and then you usually have some sort of neural network that processes the image, and then at the end you can have many things. So you could have a classifier that classifies the image into one of many classes. If you know ImageNet, that's a thing. So if there's a cat here, then the ImageNet classifier here would say cat. Or you could have something like a object detector that tries to predict on the image where the cat is, like with a bounding box. You could have a semantic segmentation where it's like all of these pixels here are cat, and maybe all of these pixels here are sky, and so it labels every pixel. There's many visual tasks that you can formulate, and they all sort of share the same architecture. And specifically, they all share this part right here. If you will, this is the visual encoder. It's usually a convolutional neural network, and what's really different between the tasks is mostly this last part here that does the actual task. But this is often called the backbone. So this is the backbone, and the idea now is, if I have a bunch of these tasks, sometimes I don't have many labels for these tasks. I don't have many labeled images so that I could train this big architecture from scratch, like in medical images or just in domains where you don't have many images. So couldn't I somehow come up with a method to create this backbone beforehand? So to create the backbone given another data set. And the simplest variant here is you take a big image data set, such as ImageNet, and then you train a classifier, like we said, to predict some classes on it. And then, because an ImageNet has a lot of images, then this is your backbone. And then whenever you have a different task, you simply take the backbone, transfer it over, and then train the other. Basically, you continue training on the other task. That's called transfer learning. The question is, how do you get a good backbone? So if you train on something like ImageNet, then this is of course a supervised task, so you'll have a very good learning signal, but even ImageNet has like 1 million images. But for example, the internet has many more images. So what you could do is you could train on this much bigger data set that you collected from the internet. Let's just call it internet. But there you don't have labels, right? So what you'll have to resort to is, instead of supervised learning, is self-supervised learning, where you have an image and maybe you rotate it to the right. So here is our cat. You rotate it to the right, and then you have a classifier that predicts that this image was rotated to the right, and then that will become your backbone. These self-supervised methods, they work very well. There is a different number of them, for example, MoCo, things like this. And there's also a number of techniques that do supervised pre-training and then transfer learning. You can maybe watch my video on Big Transfer, which is a very large attempt to pre-train a backbone for visual tasks. All right. Now, you can see right here that the sort of direction is that the more data, the better. So that's sort of the idea here, that ImageNet is a big data set. We can train a really good backbone. But, the internet is an even bigger data set. We don't have labels, so there's a trade-off. But we potentially can train an even better visual backbone to then transfer learn with. This paper goes into a different direction. They say, look, if you go in this direction right here, you get more images, but you get less information per image. So with ImageNet, at least you have the label, right, per image. But if you simply take a photo of the internet, you don't even have the label, you have to resort to self-supervised. What if we go into the other direction and we look for images that have very high quality annotations, but maybe we don't have as many? Can we do the same thing? Can we learn good backbones by trading off quality for quantity in this case? And their quantity and quality trade-off is they go for descriptions. So they'll go for something like this, where you'll have an image and you'll have a caption for the image. And so they show these on a line here, semantically dense, semantically sparse, but their task is going to be caption generation. So their task is, given an image, I want to produce a caption. And there are data sets that you can train this from in a supervised fashion, which, of course, these are very expensive to create. I mean, if you want to create an ImageNet data set, then you have to label each image. But if you want to create a caption data set, that's even harder, because a human really needs to sit down, look at the image, and in ImageNet, everything is like one class. But here you need to look at the image, and then you'll have to come up with like an adequate description. Here the adequate description is an orange and white cat near a plate and a white cake. Okay, so that's the caption right here. And of course the caption is ambiguous, so you'll have to collect multiple captions per image, and you'll have to make sure that the humans that do this do a good job and so on. So these are very, very expensive data sets, but they are very high quality. If you think of what does a single label, let's just take ImageNet. ImageNet has a single label per class. Let's say this is cat or cake for that matter. It just sort of gives you very few bits of information. But if you consider the text here, an orange cat and a white cat, an orange and white cat, you know that there is a cat, right? You know that it's one cat. You know what its color is, orange and white. Then you know that there is a white cake, right? So you know the other object. And you know the relation. They are near each other. Okay, same for here. A brown and white puppy. So this is one object and the description of the object. There are apples. There is a green lawn, and the relations between them are also clear. The puppy is lying on the green lawn and looking at the apples. So the information in captions is so much more dense than just labels. And that's the backdrop here to say, hey, can't we pre-train a backbone from maybe a small data set, but that has so much information, like a image caption data set. Okay, so their method is nothing more. They train image captioning, and then they use the visual backbone for transfer learning. So this is the model. There's an image. The image goes into this visual backbone right here, which is a ResNet 50. So this is a very, very standard convolutional neural network. And that gives you these features. So these features are 7 by 7 by 2048. This is the standard output of a ResNet 50. And then from this part on, they do a linear projection such that they can now input it into a language model. Okay, so they have visual features, and now they feed those into the language model. And the language model is just a transformer, actually two transformers. So one transformer, they're both autoregressive. One transformer tries to predict the caption in a forward way, and the other transformer tries to predict the caption in a backward way. And that's down here. So in this direction is backward because the caption has been reversed. If you don't know what a transformer is, I've made several videos on transformers. The first one is attention is all you need, and that's sort of the same kind of transformer they use here. So as you can see right here, you have this multi-head attention. the layer normalization, attention from the decoder. Now, the difference between the original Vaswani attention is all you need transformer and this one is that in the original transformer, you had, for example, if you had a machine translation task, you would have the French, maybe a French sentence over here, and then you would have the beginnings of a German sentence here, right? This is what you have already produced, and now you're asking, what should the next word be? And the architecture was such that there is a decoder transformer right here, and that there is an encoder transformer that encodes whatever you already had. And then at some point, there is this cross attention, right? There is the signal from the decoder going into the encoder and the encoder incorporating that. And then at the end, right here, the encoder would predict, or the entire transformer would predict what the next word will be. The only difference right here is that the I mixed this up. This is the decoder, this is the encoder. The only difference right here is that this encoder is no longer a transformer, but is this ResNet 50. Okay, because now you don't have an image as you can think of it like a translation task. You want to translate from images to text. Okay, so your input is going to be an image, and the signal is going like it would go in the original transformer into the decoder. It would come from the image, so from these visual features goes here. So in this drawing, this thing is going in here. And then you simply predict the next word, and you do it in both directions. And the reason you can do it in both directions here, this is not the case, of course, if you have a decoder, like a standard transformer task, because you don't need to do inference at this. You just need to do training, and training you can do using teacher forcing, and so you can do this in a bidirectional way. You don't need this at inference time. So at inference time, you simply cut off this part right here. That's your visual backbone, okay? And these features here, those are going to be the features that you then train your task on. And sometimes you fine-tune this, or sometimes you keep it frozen. You can choose that. All right, so convolutional network to encode the images. That gives you features, visual features. Those visual features go into two transformers. Both try to predict the caption of the image, one in a forward motion, one in a backward motion. And you train it to predict as accurately as possible the gold standard captions that you have in your dataset. That's it. If you train this model well, that means the model can produce accurate captions for these images, which means that it has learned something meaningful about the image, to the degree, of course, that the original caption that was in your dataset was a good descriptive caption. But we're going to assume that in these datasets this is the case. All right, that's what they do. Now, interesting thing here is that in their standard setup, they only have one of these transformer layers. So of these things right here, they only have one, and that's like, I think it's like 2,000 units wide, the hidden dimension is 2,000 units or 2,048, but they only have one layer. So what that means is that this transformer is not very powerful. So you force most of the power to come from the visual encoder. The visual encoder basically has to do most of the work, and then the transformer is going to simply be a very shallow language model on top of that. And that, of course, makes your visual backbone even better. All right, we can pretty much skip the rest. That's the idea. Like, there's nothing more to it. You train this from the beginning. You don't use any pre-trained whatever. You train this from scratch, and then you use this. And in the first experiment, they simply train a linear classifier on top of that representation. So they freeze the backbone, and then they use a linear classifier. And they compare this to baselines. So one of the baseline is ImageNet supervised, where you use the same backbone, but you train it on ImageNet in a supervised fashion. Okay, and then you use that backbone to transfer out of the text. It's kind of like what big transfer does, but just on the regular 1000 class ImageNet baseline. Then you have the sort of the unsupervised pre-training ones. So MoCo, so Perl is I won't go into Perl, but MoCo is this momentum contrast, which is one of these supervised methods that has been shown to work really, really well. And this is also, MoCo EN is trained on ImageNet, but now without the labels, because MoCo is unsupervised. And MoCo CoCo is trained on the CoCo dataset. And the CoCo dataset is what this paper here, the VirTex paper, uses. CoCo is this image captioning dataset. Now, what's important to note is that CoCo has about 10% only of the images of ImageNet. So it's considerably smaller. Now, let's see how these things fare. Right here, you can see on the x-axis the number of images, okay? The number of images that the dataset or that the pre-training method trains on. Now, of course, some of these are going to be capped because for some datasets, there are just not more images available, right? So they're going to be capped here. The ones that are training on CoCo and the ones that are training on ImageNet are going to be capped here. And you can already see that the VirTex outperforms the ImageNet supervised baseline by pretty much when you only give it this many images. Okay, so the way you do it is, in this case, you simply train these models. Now the brown one is when you take one caption per image, but the dataset actually has more than one caption per image. So when you use more than one, you can still boost your performance a bit. And that works way better than when you do the supervised pre-training on ImageNet, which would get you here with about the same amount of images. Now, when you use all of ImageNet, you can see here, you can get to a similar performance right here. But you have to use a 10 times bigger data set to get there. Right? So this already shows you sort of the advantage here. Now, also consider the difference to the unsupervised ones. So if you look at the same amount of images, the self-supervised baselines are even lower. But if you go to more images, they sort of get closer to ImageNet. And in their own papers, there are some evidence that if you self-supervised train for long enough, you can actually surpass ImageNet supervised pre-training, but I'm not so sure that that's really the case. But you can see here the trade-off between higher quality information, but smaller data sets, versus lower quality information, but more data per data set. And yeah, if you were to pre-train these self-supervised methods with lots more data, in a self-supervised manner, they would maybe end up even higher than ImageNet. Now, this graph here is sort of the same thing, where they also train a linear classifier. And you can see right here that now the ImageNet supervised baseline is outperforming VirTex by a lot. So what's happening here? Now, this here is actually, this is on ImageNet. So the task here that you transfer learn is ImageNet. Here it was like a neutral task, Pascal VOC. None of these methods have trained on Pascal. They simply have trained on their own dataset. These have trained on CoCo. This has trained on ImageNet, and then they have transfer learned to Pascal. Now the task is actually, the transfer learning task is ImageNet. So naturally, the thing that was pre-trained in a supervised fashion on ImageNet is going to have a huge advantage in this task because it basically has already learned the task beforehand. Whereas the VirTex, it has pre-trained on CoCo, not on ImageNet. And you can see if you give it the same amount of images for pre-training, it can actually, it's fairly close to the ImageNet baseline. So that's pretty respectable right there. Now, again, of course, if you use more images on the same data set that you then train for, then of course the ImageNet baseline is going to outperform it. But so pretty cool to see here that in this smaller image regime, and also consider this down here, if you go even an order of magnitude lower, it's really shining that if you have higher quality information and you make use of it, you don't need as many images. And now we knew this for a long time, but this now is showing the same for transfer learning, for visual transfer learning. So this was when we froze the backbone and then we trained a linear classifier on top. They make a short excursion here and show how different parts of their model affect their final performance. And they find that, for example, the bi-captioning, which I believe is forward and backward captioning, significantly helps, for example, compared to only forward captioning. And they also find that it significantly outperforms other pre-training tasks that they could do. And they also investigate how big their models should be. So here, this is their baseline model. Oh, I was wrong actually. It's one layer of width 1024. You can see as you make the layer bigger and bigger, that generally helps, but I guess they decided against it because the gains are too little to afford to make it worth. And also, if you make the network deeper here, you make the transformer have more layers, the performance goes up, but again, the gains are marginal, so I guess they're going to leave it away. So their baseline, as you can see, is these ResNet 50 with the one layer of 1024 size. So this is now the last task. It's the fine-tuning task. So this is what most people would do, is they would train a backbone and then they would fine-tune it on a different data set or on a different task where they don't have much labels. And here the situation looks a bit different. So if you look at, for example, a task on Coco, so there are several tasks on Coco. One of them is image captioning, which they use for pre-training. If you do other tasks on Coco, you can see right here that compared to the supervised baseline, this VirTex, it performs about the same or maybe a bit worse. But what you can see is it performs significantly better than, for example, Moco that was only trained on Coco. So again, this shows that if you have the same data set, higher quality information makes it worth it. And it's even better, as you can see, on Moco that was trained on ImageNet. It's just not quite as good as the supervised baseline. But all of them, of course, are better than just a randomly initialized network that is trained from scratch. I mean, that's the entire point of transfer learning, that you are better than simply learning from scratch. And this shows throughout this experiment, except in this LVIS masking task, where they do outperform the other methods significantly. Now, the lower numbers on this task also means that the task is harder than these tasks right here, and therefore there are more gains to be made, and therefore you could hypothesize that the more quality information that you input can be used in a better way. So maybe more complex also, the more complex a task is might also have an influence on how well the transfer learning works if you come from a high quality transfer learning task versus a low quality transfer learning task. So they lastly compare here with with Pascal VOC object detection and these iNaturalist classification, where I believe this is also a transfer learning task with fine tuning. And as you can see, they can also hold up against the supervised baseline or even outperform it at sometimes. The green triangles mean that they outperform it by a significant margin. But then on this task right here, they again lag behind. So I think the point of the paper isn't really to show that that this is the best thing ever, but the point of the paper is to show that you can go about pre-trainings. Basically, the common assumption is that you need more and more and more and more data for your model to learn about the data set. And they conclude here, no, actually, you can do with very few data points as long as they have high quality annotations. Okay, so I think that's the point of the paper. And they don't always outperform the other baselines and whatnot, but they keep the performance the same, which basically means that this is an option. Here is a pretty cool result where they visualize the attention of their image captioning model, because they train an image captioning model, and you can really see that the image captioning model learns something meaningful about the image. So when it's a bird flying, the attention is mainly on the bird, as you can see. Then over the attention widens out over the image. Air, so over the air, the attention is here in the sky and on the ocean, and then it goes near the ocean, and then the attention is on the ocean itself, as you can see. So they have a bunch of these images, and they're pretty cool here. A dog, so focused on the dog, riding on, and then you can see the attention going down because on is riding on means probably there's something below the dog. A surfboard, now the attention is fully on the surfboard. In, so as soon as you say in, the attention, as you can see, it widens out. So I think that's fairly cool demonstration that the model understands sort of the in relation, namely if it is focused on something and that something is in something else, then it widens the attention out to see what it is in, okay? The ocean, and then it focuses the attention on the ocean. So that's a pretty cool result. I guess we already knew this because we could train image captioning models before. It's just to show that it actually makes sense to use them as a pre-training task for backbones. Now, what's the future of this? The authors here in their introduction, they make a claim that this has a good future because they only train on this small data set, right? It's smaller than ImageNet, as you can see here. And they already get the same performance as if you train on the whole ImageNet data set in a supervised fashion. Of course, they're also supervised, but they have 10 times less images. And they say something to the effect of, do you know, it would be pretty easy to collect more data for this task because the internet is full of images, and mostly these images have like some text with them. They have these descriptions or they have text around it. People write something about the images. You could like mine Twitter, and then the responses when someone posts an image might tell you something about the image. But this definitely counteracts their notion that these are very high quality labels, right? Their entire point here was that these annotations, these data sets with these image captioning data sets like Coco, they have very, very high quality annotations. So this text here is very high quality. It's really a descriptive text of the image that tries to capture what a human can see visually in the image. And as soon as you go out to the internet and collect a text around images, that's not going to be the case. That information is again going to be quite low quality. And so I doubt that the performance here would hold up, or that the claim you can easily create more data for this task holds up. So that's a bit my worry about the future of this, but it's definitely cool and definitely shows this quality-quantity trade-off very well. All right, that was my 2 cents to the paper. I invite you to read it and tell me in the comments what you think about it, and I'll see you next time.